Hello, everyone. Welcome to this TCP-IP lecture course. Today we will continue the theory part of the congestion control that we started last week, and we will continue even with the second part, which is more implementation. Well, let's just do a quick recap on what we have seen last week. So, first thing that we observed was congestion collapse. Congestion collapse is a pattern that might occur in any complex system. We observe it in an example of network. In network, it is the case that you are submitting more in the network, but you end up doing more and more inefficient work, useless work, and you end up less useful work. So we are submitting more, each source is submitting more, but it receives less throughput at the end. So to avoid such inefficiency and congestion collapse, we observe that source should somehow adapt the rate to be maximally efficient. So what is the definition of maximal efficient? We observe Pareto efficiency. So we say that a collection of rate X, so it's a collection of X0, X1, and X2 in this example is Pareto efficient, it's maximally efficient if it cannot be increased, it cannot be improved unilaterally. So any increase is at the expense of another decrease. So in other words, each source has a bottleneck. In the path of each source, there exists one leak that is saturated, that is satisfied with equality rather than inequality. And then we observe that there are several allocations that are Pareto efficient. And the question was, which one we should pick? We observe, for example, if we simply maximize the total throughput, the sum of what goes out of the system, it is Pareto efficient, it is maximally efficient, but it might not be fair. It is not fair in a sense that it is at the expense, for example, in this example, to shut down one flow completely. And there was a question that what is fairness then? So we defined the first definition of fairness. It was max-min fairness. We say allocation is max-min fairness if any increase is at the expense of another decrease from someone that is not richer. So if you want to give more to someone, you should take from someone that is poor, that is richer, and that contradicts the fairness. Well, we observed that in a case that the set of feasible constraints, the set of constraints that you have is convex, which is always the case in network. This max-min fair allocation exists and it is unique. So in a network setting, we can find the unique max-min fair allocation. How? With this algorithm here, it is called water filling. So we start to water filling the sources. We start from 0, give same to everyone and increase it. Sooner or later, some sources hit the bottleneck. The user saturated link. We cannot increase their rate anymore. So we mark them as frozen. For those that are unfrozen, we will repeat the same algorithm until all of them are marked unfrozen. All of them are marked frozen. And that brought us in this quiz here. So here I'm showing you this network. So we have 4 links. All of them has the same capacity equal to C. The red flow, the flow in the top, uses 4 of the links and sends data at rate X0. We have 4 flows of type blue, where it uses only 1 link and sends at rate X1, X2, X3, and X4. Here I'm showing you 4 allocations, and I'm asking you which of these allocation is the unique max-min fair allocation in this network setting. So I invite you to join the speak up in this room here. I will open the pool now so we can share what you thought. You have 15 seconds. Well, the majority says A, which is the correct answer. So how can we compute the maximum fair allocation? So we do water filling. It is very easy in this example because it will be done in one step. So we give same to everyone. We want to find the largest possible common value for everyone. We increase the rate until we reach bottleneck for everyone here. So if we give half of the rate, C/2 to everyone, that's the maximum fair allocation in this example. But the problem with the maximum fair allocation is that it doesn't take into account how much a flow uses from a network. For example, here, the red flow is using 4 links of the network. However, each of these blue flows uses only 1 link of the network, but this red flow is receiving the same rate as others. So some people think that it is not fair. This flow somehow should be penalized for the amount of usage that is taking advantage of this network, and it should receive less. So we should give more to flows that use less of the network. That will lead us to the definition of proportional fairness. Well, the definition of proportional fairness is written here. It's a bit more subtle. So we say allocation X is proportionally fair if, first of all, it is non-negative. So it gives non-zero to everyone. And second of all, if we compare it to another allocation, X prime, this value here is non-positive. It is less than or equal to 0. What is this value here? So for each source I, we compute what is the rate of change, what is the relative change if we move from X, allocation X to allocation X prime. Then we take the aggregate. So we look at the total rate of change. If it is always negative, if for any choices of X prime, this total rate of change is a negative thing, we say that it is proportionally fair. In other words, if there exists another allocation X prime, where this total rate of change, if we compute it, it is positive, this means that our allocation is not proportionally fair. We should take X prime, for example. We should move toward that X prime. Why do we take such definition? Because it has 2 effects. First of all, it takes into account the relative share, the rate of change, rather than the absolute share. Moreover, it looks at the sum of rate of change. So with such definition, we hope that we can take into account that the usage of the network also. Well, for these 2 networks here, for the top network, for example, we already computed allocation A, which is the unique maximum fair allocation for this network setting. For the bottom network, we had allocation B, which was the maximum fair allocation in this setting. And I'm now asking you which of these are proportionally fair also. So I open a poll. So you have 10 seconds. Well, so the majority think that B is a proportionally fair allocation. Well, the truth is none of them are a proportional fairness. So let us see why. So for the first example, this is allocation A. So we want to check it against the definition of proportionally fairness to see whether it is proportionally fair or not. So what I do is I compute another feasible allocation, the x prime in the definition. How do I compute it? So I would say that I will increase the rate of each of these blue by a small delta. So instead of C/2, I give C/2 plus some delta for each of these blue flows. Then to make it feasible to respect the constraint of each link, I must decrease the same value delta from the rate of x0. This link was saturated previously, so I add a small delta here. I should decrease the same value here to respect the constraint of that link. Well, I have defined a new allocation x prime that is feasible. Now I can compute what is the total rate of change. So let's take a look at the rate of change of each source. So for this x0, the difference, the delta x is minus delta. And the rate itself was previously C/2. So the rate of change is minus delta over C/2. For each of these blue, the difference, the delta x is delta with a positive sign. And the rate previously was C/2. So the rate of change is the same thing with the positive sign, but we have 4 of them. So if we compute the total rate of change, we have computed a total rate of change that is positive, meaning that the previously allocation was not proportionally fair. So if we move toward this x prime, it would be more fair. Well, we can do the same thing for the second network. This is a network that most of you mistakenly thought that is proportionally fair. So I do the same thing. I compute another allocation that is feasible. Here, I add a small delta to each of these green flows. So instead of x2, I take x2 plus some delta. I should make it feasible. So this link here was saturated. So if I add a small delta here, I increase the aggregate rate submitted to this link by 9 delta. So I should decrease the same value from x0 to satisfy the constraint of this link. When I decrease this 9 delta from x0, this link is not saturated anymore. So that enables me to increase with the same value the rate that I'm giving to this flow here, x1. Well, this is my vector allocation x prime. Now I can compute the total rate of change, which is computed here. And you can observe, again, it is a positive value. So I could have changed the allocation to allocation that the total rate of change is positive. Therefore, it does not contradict the definition of proportionally fairness. It means it was not proportionally fair. Well, so what are the maths behind this proportionally fairness? So first of all, it's Pareto efficient. So it's maximally efficient and it has some sort of form of fairness also. Second of all, same as max-min fair allocation. In a case of networks, when we have convex constraint, it always exists and it is unique. So you can find the proportionally fair allocation in a network example. How can we compute it? Well, we should maximize the sum of logarithms of rates. If we maximize the sum of logarithm of rate with respect to the constraint, which is business as usual, coming from our capacity of our links, then we will obtain the unique proportionally fair allocation. I can give you an intuitive explanation why do we do that. The more formal and rigorous things are written in the textbook. So the explanation is if we take a derivative of this objective function, if you find the gradient descent, would be this value, which is exactly the same thing that we used in the definition. So the derivative is the total rate of change. So when this maximum is attained, when this objective function is at its maximum, then every derivative for any direction is negative, which means that we reach a point that every move that we take has a total rate of change that is not positive. Therefore, that's a proportional fair allocation. So the thing that I'm saying is very informal. So I invite you, if you are curious, you can read it more formally in the textbook. Well, and now we know what we should solve. Let's compute the proportional fair allocation for the first example that we observed. So I should maximize what? I should maximize the aggregate, the sum of logarithms of the rates. Here in this example, it is logarithm of x0 plus logarithm of x1 and etc. Subject to some constraints. So these constraints are business as usual. So each link here gives me one constraint. For example, here, the submitted rate to this link should not exceed the capacity, which means x0 plus x1 should be less than or equal to c. So you can solve such problems using convex programming, but this one has a trick. We can directly solve it. Well, the first observation is that when this maximum is attained, we must have equality everywhere. So each of these constraints must be satisfied with equality. Why is that? Because imagine, for example, this constraint is not satisfied with equality. It's a strictly less. Then I can increase x1. I can give more to x1. That does not change the other constraint, and it is still a feasible solution. And by doing so, I increase the u. It means that wasn't a maximum. Therefore, at maximum, we have equality everywhere. Now, if we fix the value of x0 to some x star, since we have equality everywhere, the rate of others, x1 to x4, would be equal to c minus x star. So if I have equality here and this is x star, this gives me c minus x star for x1. Now, if we rewrite the problem with this notion, it becomes a very easy problem. So it's a 1D problem, actually. So we want to maximize logarithm of x star plus 4 times logarithm of c minus x star. You can take the derivative, first derivative, and make it 0. That gives you c over 5. So that gives us the unique proportionally fair allocation in this example, which is exactly what we were interested in. So in proportionally fair allocation, we are giving much, much less. We are giving 1/4 to x0, the flow that uses more of the network compared to flows that are using less of the network. Well, now it's time for a quiz. So for another famous example that we already seen several times in this lecture, I'm giving you 4 allocations, and I'm asking you which one is the unique proportionally fair allocation. So let me open the pool. So you will have more times for this quiz. Well, I will close the poll in a second. Well, it seems that we fixed the problem. So we have a majority of the correct answer, which is B. So let's see why. But it's true that to solve this problem, to find the proportional fair allocation, maybe you need more time to write things down and maybe a calculator. But since we have 4 options, with some reasoning, we can guess what is the correct answer. So allocation A, we already checked this. We check it against the definition of proportional fairness. We know that it's not proportionally fair. What about allocation B? Well, allocation B is not even Pareto efficient. It's not maximally efficient. Therefore, it cannot be a proportionally fair allocation. Why is not a Pareto efficient? Because because this thing here is not saturated. This blue flow does not have a bottleneck. Therefore, I can improve this allocation unilaterally. I can give more to X1 while not impacting the others. Therefore, it's not Pareto efficient and it cannot be a proportionally fair allocation also. Allocation C and D are Pareto efficient. But if you look at the allocation C, you will see that it's going in a wrong direction. So the purpose of this proportional fair allocation was to give less to someone that uses more of the network. But here we are giving more to X0, a flow that uses 2 links of the network, compared to X2, a flow that uses 1 link of the network. Allocation D is a Pareto efficient one and also is in the right direction. It's giving less to X0. So it's probably the correct answer. How do we compute it? So we do the same method that we observed a minute ago. So I want to maximize the sum of logarithms of each rate. Again, here with the same explanation, we must have equality everywhere. Now, if I fix the value of X0 to some X star, I will obtain these values for X1 and X2. Then the problem becomes a 1D problem. Again, I take the first derivative, make it 0, which gives me this value for X star, which is the allocation D. Another thing that is important that these proportionally fairness can be interpreted as what we call utility fairness. So it's a known thing in economy, but what is utility fairness is we maximize a global utility. So we take a utility function UI for each source, we apply it to that rate, and we maximize the aggregate. In a case of proportional fairness, this UI is identical for every choice of I, and it is simply a logarithm. Then, for example, if I plot this U function, is the logarithm function. I can take another utility function. For example, I can take this red curve here, which is 1 minus 1 over x to the power of m. It can be shown that if m is large, taking such utility function and maximize the global utility gives you something that is very close to the max-min fairness. Max-min fairness is not a utility fairness, but the limit goes to something that is very close to max-min fairness. Well, until now, we have seen that if we let sources to send at whatever rate they want, we might have congestion collapse or congestion inefficiency. To avoid that, we should adopt the rate, and it is called congestion control. So this rate adoption should be maximally efficient and should target some form of fairness. We already observed max-min fairness and proportional fairness. But now the question is, how congestion control can be implemented in a network setting? Well, in general, we have several ways to implement congestion control. The one in the internet, the TCP congestion control, is called end-to-end. There are other ways, for example, explicit. Explicit is whenever you're connected with your phone to a base station, the base station frequently tells you explicitly to send at what rate. That rate depends on the subscription that you have, how much monthly you pay for those subscription, and also the busyness of the network. There are other approaches, fair queuing per flow, you will see in the next lecture. What is done in the internet? What is the TCP congestion control is end-to-end. It's like source start at a small rate and they taste the water. What it means, they taste the water, they send at some rate. If they receive a positive feedback, they increase their rate. If they see negative feedback, if bad things happen, they decrease their rate. But let's see more on that. So on October of '86, when the first congestion collapse happens, I told you that there were other companies called, for example, DECnet, that already thought of congestion control mechanism, and they already implemented some mechanism that worked perfectly fine. So at that time, DECnet was using 1 bit, which is called DEC bit, in their congestion control mechanism. And that is actually what is done in the internet afterwards. So the idea is that the network provides a feedback, which is actually 1 bit. So it's either 0 or 1 to the host, to the sources. And depending on that feedback, hosts would react. They increase or decrease their rate. Here in this very, very simplified example, where we assume that we have our network is basically 1 link. So we can imagine as a 1 bottleneck link with capacity C. So whenever we are below the capacity, the network provides a positive feedback that is 0, meaning that hosts could increase their rate. And whenever we go beyond the capacity, we receive a negative feedback, a feedback that is 1, meaning that we should decrease our rate. Now the problem is what form of increase and decrease law we should take. Well, let's take the easiest one, which is linear loss. If we receive a negative feedback, we should decrease the rate with linearly. So if I assume that the time is discrete, so if I'm at time t and I receive a negative feedback at time t, for the next decision time, t plus 1, I should have a smaller rate than my previous rate at time t. So this is this value here. So if I want to decrease, I should have 1 multiplicative decrease factor that is less than 1, and 1 additive decrease term, which is a negative 1. For example, I take the half of the previous rate minus 1 megabit per second. Same thing, if I receive a positive feedback, I should increase my rate in the next decision time, which I use the previous value to do the change. So I take 2 other coefficients, which are larger than 1, and the additive increase term is positive. Well, we have 4 coefficients to decide on. So let's take an example, these 4 coefficients. So here, if I receive a negative feedback, I decrease the rate by doing what I call multiplicative decrease. So I make the rate half of what was the previous value. Whenever I receive a positive feedback, I do additive increase. So I add 1 megabit per second to the previous rate. Here I'm showing what would happen in this example. So here we have the same example. We have 1 link. It is shared between 3 sources. Source 3 is silent in the beginning. So at first it's shared with only 2 flows. So what I expect, since it's a very small example, to be maximally efficient and with whatever fairness that you like, this link should be shared equally between the sources that use it. So at first, I would like to have to give half of the capacity to 1 and half of the capacity to 2. Here I'm plotting the rate of each source. So this is the rate of x1, x2, x3, and the x-axis is time. Well, first x1 starts at a small value, x2 starts at a higher value. We are above the capacity. They both receive a negative feedback. They decrease their rate. Now we are below the capacity. They receive positive feedback, so they increase their rate. And after a number of iterations, they converge to more or less the half of the capacity, which is 10 here. As you observe, when they converge, they start oscillating over the converged value because they always want to get more. They receive a negative feedback. Now they have less. They receive a positive feedback, and they oscillate over the converge value. So we are maximally fair and maximally efficient. Sometimes we go above the capacity, which is fine. We can tolerate it by doing some buffer management. Well, what happened if something changed in the network? For example, at time 100, I have another source that kicks in. So ideally, I would like that this mechanism automatically detect it and adopt the rate. So it does actually. Well, when this source kicks in, so we want to make some space for himself. So everyone receives a negative feedback because we are going above the capacity. So everyone reduce the rate, and after a couple of iterations, they converge to the 1/3 of the capacity and oscillate around it. So it seems this for coefficient that I chose is working. Now let's see how can we choose these 4 coefficients for our linear loss here, because we want to be maximally efficient and target some form of fairness, the maximum fairness or proportionally fairness. Well, first, let's see what are the moves. So let's define the problem specifically. Let's zoom on the case that we have only 2 sources. Here I'm plotting the rate of x2 in the y-axis and the rate of x1 in the x-axis. So we have line with capacity C. Therefore, the aggregate submitter rate to this line should be below the capacity C. That gives me this line. So any feasible solution is below this line. And if I want to be maximally efficient, I should be on the boundary of this line. What is fairness in this example? As I said, equality is a fairness, since it's a very simple example. That gives me another line. And ideally, I want to be maximally fair and maximally efficient. So I want to be in the intersection of these 2 lines. And this is the target rate. Now imagine that at some point we have this value for x1 and this value for x2. This gives me this vector x. And I want my mechanism, my linear loss, to make me go from this point to the target value here. Well, if you think about it, since we are below the capacity, so we receive some positive feedback. We do some moves to increase our rate. Whenever we go behind the capacity, this line here, we receive some negative feedback to force us to go below the capacity, and hopefully with some iteration, we will reach the target. So let's have the same dictionary. Here I'm proposing 2 moves. So at this point, if I have this vector x, I can take 2 moves. One is the blue arrow number 1. One is the green arrow number 2. One of them is additive increase. One of them is multiplicative increase. And I'm asking you which one is which. So I will close the poll in 10 seconds. Well, we have a tie between A and B. So let's reveal the answer. So it's a geometry question, right? So if we are at this line and we do a move that we keep in the same line, meaning that we keep the same angular distance it is only a multiplicative increase. So we only multiply it by, for example, 2. However, we can check that the other one is additive increase. We add a constant vector. We increase the values of each coordinate by a constant. Therefore, we do such move. So one is additive increase and 2 is multiplicative increase. Well, back to our problem. We have 2 linear laws, one for increase, one for decrease, and these are 4 possible cases that we can have. Well, let's first take care of the decrease. So we should take multiplicative decrease or additive decrease. Well, what is the target? The target is here. So I want to be fair and maximally efficient. Additive decrease only worsen the fairness, make me further from this target here. What about multiplicative decrease? Well, it doesn't make things good, but at least it keeps the same angular distance with the fairness. So the decrease must be multiplicative. What about the increase? So if you take the multiplicative increase, it's like this multiplicative decrease. It doesn't make it more fair, actually keep the same angular distance with the fairness. And additive increase is the only hope to get more, to reach the target. So the increase must be additive. And that is exactly what is done in the internet when the first congestion collapse happened. It is called AIMD, additive increase, multiplicative decrease. And it tends to bring the allocation towards fairness and also being maximally efficient. Well, so we talk about max mean fairness, talk about proportional fairness. Now I'm asking you, if I implement AIMD, what form of fairness I will achieve? You have 10 seconds. Well, we have, so ABC, all of them are chosen. We choose somehow all of them are a correct answer. So if we do AIMD, we reach something that is between max mean fairness and proportionally fairness. It's closer to the proportionally fairness. So if you remember the utility fairness, it can be shown that AIMD is actually a utility fairness, where the utility function is this function here, is the logarithm of the rate divided by R. R is the additive increase term. For example, it's 1 megabit per second, plus eta times the rate. The eta is the multiplicative decrease term in internet is, for example, half. Well, and this gives us this blue function here. We already observed that proportionally fairness is also a utility function where the function is logarithm, simply logarithm. And if we take the black curve, a function that is very close to the step, we will achieve something that is very close to max mean fairness. You should be careful here. I plotted these utility functions are plotted to be fitted in this network, so they are rescaled. If you rescale a utility function, that doesn't affect the allocation itself. And as you observe, the AIMD is between the proportionally fairness and max mean fairness, closer to the proportionally fairness. Well, the congestion collapse happens. They implemented AIMD. That was a congestion control, but that caused another problem. What was the problem? Well, in the example that we observed, at the time that source 3 kicks in, so we want to share the bandwidth now with 3 sources. And this is what happens. So source 1 and source 2 have the same value. They were iterating, they were oscillating over the converged value, and source 3 kicks in. And after a couple of iterations, we converge to the desired value, 1/3 of the capacity. In the left figure, I'm plotting source 3 as a rate of source 3 as a function of source 1. And you see it requires not too many iterations to converge to the same value. That's why they want to accelerate this convergence. They use additional mechanism, which is called a slow start, used as the beginning of a connection to accelerate this convergence. So what is this a slow start? Where it's called a slow start, but in fact it's a fast start. So at the beginning of the connection, a host should target some maximum rate. So this maximum rate is what you can do, what your capability is, presumably with the fixed maximum window size of TCP. So this source targets its maximum rate and it starts at a slow rate. So that's why it's called a slow start. But it increases its rate exponentially. So at the beginning, the increase is multiplicative. So whenever we receive a positive feedback, for example, we double the rate here. The factor that I'm taking is 2. Therefore, we increase our rate exponentially. We are very fast. However, we want to be very conservative. We don't want to hurt others. We don't want to be inefficient. Therefore, whenever we receive a negative feedback, we stop increasing. We are back to the very small rate. And these negative feedbacks gave us some information about the condition of the network. So this rate here is more or less what I can achieve from the network. And since I'm very conservative, I take half of that rate as my target rate. So now I start from a slow and target half of the rate that I receive a negative feedback previously. Again, I increase my rate exponentially until I reach that target rate. And then I exit the slow start and continue with AIMD, additive increase, multiplicative decrease. This is an algorithm here where you can read it yourself. And in the same example, when we implement the slow start, you see that it really accelerates the convergence with only few iterations. We converge to the value, then we exit the slow start and we continue with AIMD. So this is a comparison. Without a slow start, we will require a number of iterations. Whereas by implementing the slow start, we accelerate this convergence. We only a few number of iterations, we converge to the value. Well, that was what we wanted to see from the theory part, the core part of the congestion control in the TCP on the internet. In the second part, given by the professor, you will see more refinements and the implementation point of view, how it's really implemented in TCP-IP. So I would like to thank you for listening to me. It was a great pleasure for me to be a part of the lecture team in this course also. And I would like to ask you a favor. It would be a great help for me if you can provide your valuable feedbacks on my teaching. I created a Google form. It is available on the Moodle, and you're more than welcome to go there and fill in that form. It's a very small form and take you 1 or 2 minutes at most. Then thank you very much.
We're ready to restart. So thank you, Hossein, for explaining us what the theory is. This is showing a congestion collapse in a road system. That's a true picture. The throughput of this intersection is quasi-zero because some cars are blocking other cars. That's in Paris, where people are notoriously not very well disciplined. So that is what happens. And the goal of congestion control in the internet is to prevent this from happening, as we have just learned, and also to be hopefully maximally efficient, perhaps close to proportional fairness. So how is this implemented in the internet? This is the topic of today and the beginning of next week. So the first thing to realize is that in the internet, congestion control is put in TCP. That's a design decision that came after the fact. When TCP was designed, it was meant to be a transport solution that provides reliability, repairs packet losses, and provides this wonderful socket interface that we know how to use. Then, after the congestion collapse, the historical congestion collapse in the internet, people realized, oops, we have a problem. There's something we didn't think about, which is this congestion problem. And the question was where to put the solution. And the natural place to put it, by observing things that were done in other networks like DECnet and IBM SNA, had the concept of sessions. You would not simply send best effort like we do today in the internet by sending a datagram, connectionless. You would first establish a relationship between the two ends and agree on a window and things like this. All the other competing networking protocols had that. And then the internet realized, oh, but we have that if we use TCP. If we use UDP, we don't, but if we have TCP, we have that. So let's put it into TCP. And the UDP traffic, well, we'll take care of it separately, as we will discuss. At that time, when this happened, most of UDP traffic was very small volume traffic. You send a request to a DNS server and you get the reply. There is not much you can do in terms of congestion control about that, because by the time you receive feedback, probably the interaction is over. So you cannot really congestion control the very short flows. It's only the flows that send perhaps a few packets that can be subject to congestion control. So that's the first element. Congestion control in the internet is in TCP. Now, in congestion control, why do we do that? How do we do that? Well, a TCP source adjusts its window to the congestion status of the internet. We've seen that a TCP source adjusts its window based on the window advertisement sent by the other end. It will also do it based on orthogonal issues, as we will see, using the techniques that Hossein has explained, additive increase, multiplicative decrease. Now, in those techniques, we need a negative feedback. We need a congestion feedback. Other protocols, like the ones I mentioned before, they had thought of this problem, and they had a negative feedback, which was, for example, the DEC bit, which was the most popular one. TCP-IP did not have it. So the idea here, which is probably not the best idea of the TCP/IP architecture, was to use losses as a negative feedback. And we will see that how we are trying now to get out of this decision. But that was the idea, which seemed like a good idea at the beginning. They wanted to save the situation by saying, we did not think of congestion control. We built this very complicated thing, and we did not think of one issue. If those people had been designing planes, they would have crashed first. So here, there was no severe damage to anyone. But there is a problem of absence of feedback. And then the most natural thing to do is to, well, use something that exists already. Since we use TCP, if I receive acknowledgements, that means there is indication that everything is happening smoothly. If I don't receive acknowledgements, then perhaps the packet is lost, but perhaps it's lost because due to buffer overflow, which is the primary indication of congestion. So that's a very important design decision. The negative feedback in the internet is loss. Now there still are UDP sources, and today when we use very low latency interactive audio and video for video conferencing, for example, journalist, professional, low delay video conferencing, they use UDP. And then it's not like the UDP that we thought of 30 years ago, that is for very short interaction. You can have very long sessions. Then you have a problem. What happens in the network where you have a lot of UDP traffic that is not congestion control? Well, the answer is UDP sources should also do something. And the dogma today is, since TCP solves, we know how to solve the problem in TCP, UDP sources should imitate TCP. This is called Tcp Friendly Sources. We'll see how this can be done in a few more slides. And there are some UDP sources that implement, they do not imitate, but they implement exactly the same code. For example, when you do a transport solution like QUIC, which is on top of UDP, then you do the same thing as TCP. So let us see what TCP does. We mentioned already when we discussed the pure transport layer function of TCP that there are zillions of options in TCP. In congestion control is the same. There's lots of versions of TCP. Many of them are experimental, have been designed by researchers, some by Google, some by some by Microsoft, for example. And we will see the ones that have survived the evolution today. TCP Reno, which is the historical version. TCP Cubic, which is the most widespread version that we find in all the Unix type environments. Data center TCP, which is used in data centers, and TCP BBR, which is the last child of this family, which was launched by Google, has a few problems, but still is very widespread today. So historically, the very first version of TCP, which is still present in some form in practically all other versions except for BBR, simply implements the two ingredients that Hossein has explained to you: additive increase, multiplicative decrease, corrected by slow start, because we know this additive increase, multiplicative decrease is too slow at the beginning or when there is an interruption. So we complement it with slow start, which is in fact a fast start. Right? It is slow start compared to starting at full speed, but it is fast compared to doing AIMD. Now, between what we see in theory, AIMD, and what we do in TCP, there is a problem. We need to match the theory to the language of TCP. In theory, we have a source that sends at a given rate. Now, what is the rate? TCP is not rate controlled. TCP uses a window. So we will have to map the rate to the window. And this is based mostly to this formula that says that we have seen when we talked about TCP, where if you have a sliding window mechanism and the window size is W, in the good situation when there is no loss, the rate you obtain is the window size divided by the RTT. So you can control the rate by this. This is an approximate formula. It works at a macroscopic level when there is no loss. Now, when there are losses, of course, the formula is no longer valid. So this explains why in TCP there is complexity in handling the cases when there are losses here. As I mentioned, the negative feedback is a loss, and the positive feedback is when an ACK is received. So we do additive increase, almost. We'll do a bit less than that. And the idea is we add by one packet. In the language of TCP, a packet is a segment, so it's a maximum segment size, 1 MSS per RTT. So we increase every RTT by one packet. So that's the V part of the additive increase multiplicative V0, and the multiplicative decrease is 50% here. So that is the parameters that are in TCP Reno. We'll see that TCP Cubic has slightly different parameters. And the slow start doubles the window every round trip time. Slow start is run at the beginning of a connection and whenever there is a loss detected by timeout. The idea that's behind that is if a loss is detected by timeout rather than by fast retransmit, it is probably a very bad situation. The congestion is severe. That's the intuition behind, or that's the assumption behind it. If you have a very bad situation, it's better to do slow start. If a loss is detected by fast retransmit, we do the truly AIMD. We decrease the window by 2 using a mechanism which is fast recovery that I will explain next. So how is the multiplicative decrease implemented? Whenever there is a loss, we decrease the window by 2, but as we will see, if the loss leads to slow start, we've seen that within slow start, we do something else. We start with the smallest possible window, increase it exponentially fast until we reach the target value, and the target value is half the value that it had before. So congestion window, I should have mentioned this, of course, is that congestion window is a variable that is associated by TCP to every TCP connection. So every TCP connection has the offered window, that we have seen already. In addition, it has the congestion window. And the true usable window is the min of the two, which is new. Before we had done as if the offered window was fully usable. Well, in fact, no. When you start a TCP connection, you are in slow start. The congestion window is the minimum value, 2 packets. Then that's the beginning size of the usable window. Even if the offered window is huge, the congestion window comes to play, and you take the minimum of the 2. And this congestion window is believed by TCP to be reflecting the current rate that this connection can send. Congestion window divided by Rtt reflects the rate that you can send. If there is a loss, we do division of this by 2, and the window is divided by 2. But as we have seen in slow start, the immediate window is not exactly this one. That's the one we will have at the end of slow start. So this is how multiplicative decrease is implemented. Additive increase is not exactly implemented, but is approximated by this formula here. For every ACK that is received, you apply this formula. You increase the congestion window by this increment, which is a bit mysterious. Why is there a square? But it becomes less mysterious if you change the units. If you consider that my data unit is an MSS, one MSS is 1 unit, then the increase of this window is you increase the congestion window by 1 over the congestion window, which is a naive way of saying that if I do it congestion window times, I will increase by 1. In fact, you will not do that because the congestion window itself will move a lot, but that is the intention. This is illustrated by this diagram. So remember, the goal of the additive increase is that every round trip time you increase by 1 MSS, which you could do in this way by having a timer that ticks every round trip time. But since the round trip time itself is something that's very variable, we don't do it in this way. Instead, whenever we receive an acknowledgement, we apply this formula. If we started with a window that was 1, then we say 1 plus 1, that's 2. Then when the window is 2, we receive an acknowledgement. We increase by 1 over 2, which gives 2.5. If we receive an acknowledgement a little after, then we increase again by 1 over 2.5, which makes the window 2.9, etc. So we see that we increase, roughly speaking, by a little less than 1 when a full window is received, which takes a little bit more than an RTT. So this is a bit less than additive increase, slightly less than additive increase. That's one implementation. That's the classical implementation of TCP New Reno. There are other implementations that are more strictly doing 1 congestion window by 1 MSS, but we won't dive into those subtleties. The multiplicative increase is implemented only in slow start. Of course, we know from the theory of AIMD that the increase we should do in order to improve fairness is additive. But during slow start, we still do multiplicative increase. And the way it's implemented is in a similar way. For every acknowledgement that you receive, you increase this window by 1 packet here. So this is illustrated here. We see after receiving 1, the window becomes 2. After receiving those 2 acknowledgements, the window becomes 4. So this is truly an exponential multiplicative increase, not for every round trip time, but for every time it takes to receive and acknowledge a full window, to send and acknowledge a full window. So this is very close to the multiplicative increase, and this is how TCP does its slow start. So this is illustrated here, the life of a TCP connection that has only losses detected by timeout. On the y-axis, I'm showing the congestion window size, and on the x-axis is time. We see that we start with slow start, exponential increase, with the initial value of the window. Whenever there is a loss, we divide by 2 this value. We start again until the slow start finishes. Here, I'm showing a not very typical case, but not impossible case either, where there are losses during slow start. So here we see the reduction by 2 of the target window. And here we exit slow start. And here we have this almost linear increase of the window size that increases slowly, almost linearly, during as long as we receive acknowledgement. This is called congestion avoidance in TCP parlance. Here is a loss that's detected by timeout. So we see that we divide by 2 the window, but we don't immediately implement the window. Instead, we go into slow start, which starts with a very small window size, increases exponentially until we reach that value. and then we do additive increase again. So here we have an alternation of additive increase, reduction of by 2 of the target window, and slow start phases. So this is how TCP implements additive increase, multiplicative decrease, and slow start. But most losses are hopefully not detected by slow start, but other heuristics, we've seen a number of them. Fast retransmit, in particular, is associated with a different way of handling the congestion window. And the reason is that, as I mentioned, first, when the loss occurs detected by fast recovery, ideally, what we should do is reduce the rate by 2. We should not go into slow start. We should simply reduce the congestion window by 2. Or more precisely, we should reduce the rate by 2. Now, the problem is that the congestion window is not exactly controlling the rate. It's doing it when there is no loss, but now there is precisely a loss because we were detecting a loss. And the problem is easy to understand. If you have sent 10 packets and the congestion and you have a loss, then if it's the first packet of the window and the window is 10, if the first packet of the window is lost, the loss of this first packet prevents the window from moving. So you're blocked, in fact. So your sending rate is 0 with a single loss. So there is a discrepancy between controlling the rate and the window mechanism. It works as long as there's no loss. When there are losses, then things are a bit more complicated. That's exactly the problem that this heuristic, which is called fast recovery, which goes always together with fast retransmit, that's the problem that this one is solving here. So and it's solving it in a completely ad hoc way. People have done a number of NS2 simulations and found that it works well, and that's the only theory we have about that. So the way it works is that, like in slow start, the window is divided by 2. We do the multiplicative decrease, but the congestion, but we put that into the slow start threshold, like a variable where we remember this value. The congestion window instead will be allowed to increase, in fact, below the target window until the loss is repaired. In order to address this problem that I said before, that if in the worst case it's the first packet of the window that is lost, in fact, it's as if your window would be 0. So the congestion window, and you should increase the window if you want to have a rate that is non-zero. So the heuristic is given here. When a loss is detected by the conditions of fast retransmit, you divide the current window size by 0.5. You put that into a variable that you remember. And the congestion window becomes this value here. You take this plus 3 packets. And then you will start an exponential increase. For every acknowledgement that you receive, you will add 1 packet here until you reach a maximum value. So in fact, you do an exponential increase, a bit like slow start, but not starting from 0, starting from half plus 3. Now, why is half plus 3 a good number? I don't know, but this is what is done. You do this until the loss that was detected here is repaired. And when the loss is repaired, as usual, starting with this value. Here is an illustration. I have here a source on the left, a receiver on the right, and I am sending packets. So we see the value of the congestion window is 800. So here, to simplify the story, every packet has size 100. So we can send here packets 200 to 800 if we start from scratch here. And the second packet here is lost. Now, this loss is not yet detected. So the congestion window is still 800. And here we receive an acknowledgement that allows us to increase the window by this formula, 1/800. So we increase the window slightly. And if we receive many acknowledgements, that would lead to a quasi-linear increase. So we continue to send, but at some point here, when we receive 3 duplicate ACKs, at this point here, line 12, here we detect the loss. Fast retransmit is exercised here. So here we will apply this mechanism here. We divide the congestion window by 2, round it to an integer that gives this number here. That's the target window now. And the congestion window is this plus 3 segments, that's 700. Which allows us to send the missing packet. That's what we do when we detect a loss. We retransmit the missing packet. Here, all packets have the same size, so the story is easy, but as you can easily imagine, things might be more complex. A packet that was sent might be smaller than the MSS. We ignore those details. And here the window is large enough to allow me to send one more packet, which was the goal. We don't want to set this source to 0. We want to reduce its rate by half. So we allow it to continue to transmit. And if the loss was truly isolated, which is the assumption behind this mechanism, we see that the loss will be repaired here. So sending this packet will repair the loss. And when we receive here this acknowledgement, the loss is repaired, and we exit this fast recovery phase. And we see that whenever we receive acknowledgement during the fast recovery, we have an exponential increase of the window, 800, 900, 1000, which will allow us to continue sending until, of course, we receive the loss that is repaired. So this is a heuristic to avoid blocking the source here. At this point, we have exited slow start, fast recovery. Now, question, at this point here, how many packets can this source send? Here. Speak up on this number. I close the poll in a few seconds. Closing. It's almost a tie, but the correct answer is C, 3. We can easily see this if we look at what has happened here. So now the acknowledgement is 900 and the window size is 400. So in round numbers, that means we can send 4 packets. 4 packets starting from where? Well, from the acknowledgement. So from this number, we can send 4 packets. 1 has been sent already, so we can send 3 more. That's the correct answer. Okay, we have discussed losses, but the losses may be due to congestion or to other reasons. For example, on wireless technologies, losses may be due simply to errors of the decoder because the channel is random. The Bluetooth channel between this and my thing here is always changing because I'm moving around. And so the channel estimation is not perfect. So no matter how hard we will work in wireless technology, there will always be some losses here. What happens when some packets are lost in spite of the Wi-Fi retransmission? We've seen that Wi-Fi requires an acknowledgement to be sent and resends it, but once in a while, that retransmission might fail. What will happen in such a case? What will TCP do? What do you think that TCP will do? I close the poll in a few seconds. Closing. And of course, the correct answer is B, unfortunately. If TCP is at the source, when TCP could know it's a loss due to Wi-Fi, so it could do something, but in practice, it's never done because TCP is in the operating system, the Wi-Fi is hardware. They usually don't exchange that kind of information. Also, it could be that TCP is the Wi-Fi link is not at the source. Perhaps I access the Wi-Fi link over another link, which is not where the loss is occurring. So the TCP source will simply see a loss and will go into one of the mechanisms we've seen to reduce its congestion window. So we'll reduce its sending rate. So you have double penalty. If you are over a wireless link that is not too good, then you have not good performance because the link is not good. But in addition, your TCP, your internet traffic will be constantly congestion controlled. So we'll have a low rate simply because of that. Imagine, for example, you're competing over the internet with other people who are not over this Wi-Fi link, but there is another bottleneck, for example, on the server side somewhere, then you will be penalized. Simply, you will get less of your fair share simply because of those many losses. That is one of the problems that exist today in congestion control. We will see a solution to that, a partial solution to that. Wireless operators are trying for cellular networks. For Wi-Fi, nobody cares, it's your problem. But for cellular operators, it's the problem of Swisscom or Sunrise. So what they propose to do is to deploy what we will call ECN, and we'll see in a few more minutes, but that will still not take care of everything. In particular, the only solution is try to avoid as much as possible wireless losses. A way to avoid wireless losses is to have very dynamic variable coding. You code, and the rate at which you can send information can vary dramatically. If you have a suspicion that the wireless channel is becoming less good, then what you do is simply reduce the speed at which you send information by adding a lot of redundancy. That's a way to avoid this problem that must be implemented for high quality networks. So what does TCP, this version of TCP, which is called TCP New Reno, what does it implement in compared to the theory that we've seen with Hossein before? We've seen that if we can do max-min fairness, or we can do proportional fairness, or we can do AIMD, and we've seen that AIMD leads to a form of utility fairness that's somewhere between max-min and proportional fairness. Well, TCP Reno is practically, it's not exactly, but it's very close to that. So of course, the details here depend on the particular parameters of a TCP connection, in particular, its round-trip time. But the take-home message is that the fairness of TCP is intermediate between proportional fairness and max-min fairness, which is not so bad, given the difficulty of implementing something exact in software systems. It means it's not so bad. We know proportional fairness is perhaps the most desirable one. Max-min is also not bad, but has efficiency problems. So is a bit too extreme. So this is, in some sense, good. However, this is for sources that have the same round-trip time. Here, the utility function that I'm plotting depends on the round-trip time. Now, what happens when the round-trip time varies? Here, I'm plotting the utility function of, which is given by this formula here. One of the formulas, the one that was displayed in the previous slide. Now, in the previous slide, I plotted the utility function, the rate on the x, and on the y, the utility function. So TCP will try to give a rate that is as good as a utility that is maximal, but since it is concave, it will stop at some point, and this is what makes the thing close to proportional fairness. Now here, I'm plotting the same function, but on the x-axis, I put the round-trip time. How does this function, which is here, given by this formula, and under simplifying assumptions that the utility of TCP New Reno, how does it vary as a function of the round-trip time? Well, there is two contradicting arguments, one over tau here and tau there, but arctangent is concave, so this increases less fast than that. So if we compute the derivative or simply plot it, we will obtain a curve like this. So the utility function is decreasing as a function of the round-trip time. What does it mean? It means that we can reason, at least in a simplified model, as if all the TCP connections that are implementing TCP New Reno, they are collaborating. In fact, they are implementing a distributed solution to solving an optimization problem, which is maximize the sum of the utility functions of all TCP sources. But the utility function now depends on tau. If I have a large tau, what does it mean? It means that for a given rate here the rate x is fixed, my utility decreases. So if you're the optimizer, you're the social planner, and you have finite resources, which are the capacities of all the links, you have to give rates to the different sources in order to maximize the sum of all utilities of all your network here. If a guy has a very small utility function, then you will give less to that guy. You imagine utility is payment you receive. You give to the social optimizer, you give 1 franc per unit of utility. You will maximize the total number of francs, so you will maximize the sum of the utilities. But if I have a very small utility, I should not be given a large rate, because giving a large rate to me is a waste. You could give this large rate to someone else who has a higher utility, who will pay more. Right? So you will sell more to those who pay more. So a utility that is small means you will get less also. I will skip this one because I gave the solution. We can immediately solve this. Here I'm showing a very simplified but not so contorted example where I am accessing a bottleneck link over access networks that have different RTTs. That's the kind of things you will do in the lab when you will study congestion control in lab 5. Then we can easily do in Mininet that kind of things. Of course, the network is always more complicated in reality, but that's a reflection of what happens when you have a bottleneck link here. And here you could assume you have an access network that is different depending on where you are. So here I'm accessing the network over 20 milliseconds with a one-way delay of 20 milliseconds, or here 60 milliseconds. But the bottleneck is here between the router and the destination. Now assume they both send to the destination here. Since the round trip time of S1 will be smaller than the round trip time of S2, and if S1 and S2 are the only two ones sharing the bottleneck, the sharing will be done, as we have seen before, by maximizing the utility function. Therefore, the result of this distributed optimization problem will be to give more to S1 than to S2, because S1 has a higher utility function for a given rate. Which means that if you access a congested network or bottleneck, there is always a bottleneck somewhere in the internet. If you access the bottleneck link from closer, you get more. That's the bias of TCP, at least the standard version of TCP, against long round trip time here. So this Rtt bias is known and is sometimes you read stupid things about this. So in order to avoid saying stupid things, let's discuss the two aspects of that. Part of that bias is correct in the sense of proportional fairness. If I am accessing the network and I'm using a large number of hops, then I should get less. That's the proportional fairness story we saw before. In the example you saw with Hossein, you had the source 0 that was accessing all the links, and with a proportionally fair allocation, it was getting less. So in that sense, it is true. If you are further away, if you're accessing from very far, you use more of the network, therefore you should receive less. This is partly true only because in reality, this is not what is happening here. You get less not because you are accessing more congested resources, but simply because your RTT is larger. And your RTT, in the example we saw for proportional fairness, all the links were congested. All the links were fully utilized. So in such a case, yes, if you use many bottlenecks rather than one, you will get less. That's proportional fair, and it's okay to be proportionally fair, but it's not okay to give less simply because one of the links is longer here, which is the bias against large RTT. So it's an undesired bias in the design of TCP renal. We have seen an abstract explanation of that. I've explained with utility functions, arctangent function, but there is also a mechanical way of understanding why. If you think about how we implement AIMD, the additive increase is 1 packet per round trip time. So you have a short round trip time, you increase linearly, but at a rate which is larger than someone else. The decrease is the same, but the increase is larger. So of course, at the end, you will get more. So you will not have something desirable here. We can go one step further and analyze what is called the mechanics of TCP renal in the form of the loss throughput formula. What does it mean? If I consider a large TCP connection, when large, it's in time or volumes. Of course, if I'm sending 2, 3 packets, spend most of the time in a slow start, and the performance will not be given by this formula. There are formulas for that. But here, if we assume we have a long-lasting connection, you do a Zoom session, for example, what is the rate you get in average for your TCP connection? Then it's intuitively clear that it should depend on the proportion of drops that you see, because the only feedback that you receive from the network is packet drops. If you receive a lot of packet drops, you receive a lot of negative feedback. That's a signal that the network is congested, and therefore you will receive less. If you receive very few losses, then your rate will be larger. If you receive 0 loss, then the rate will be as large as the maximum limit given by all your elements of your system, by the limit of the speed at which the bus of your machine is able to run, the maximum window size that TCP is able to give, etc. You will have the maximum if there is no loss. But if there is a loss here, the rate that you achieve should depend on the loss probability, which is given here by this parameter Q. And there is a simple approximate formula that is given here. The derivation of this formula is given in the lecture note. It consists in analyzing the additive increase multiplicative decrease. So we analyze a long period and we count how many things are sent. We divide by the length of the period, and that will give something like this. So Q is essentially the number of times, the number of packets that lead to a decrease here. So this formula is expressing exactly the bias against the RTT. We see that the bias is in fact in 1 over RTT. It expresses also other things. The packet size also plays a role. We had forgotten about it. If you have a larger packet size, since you increase by 1 packet at every the additive increases by 1 packet. If your packet is 500 bytes or 1200, you increase by more. So that's another reason for having a large packet size here. And this formula, as we will see, is interesting because it's implemented in other mechanisms here. For example, back to the example I gave before, we know that S1 will get more than S2. Assume S1 and S2 are sharing this bottleneck here, because TCP is achieving some form of utility fairness. We know it's Pareto efficient. So it will achieve the rate of the bottleneck. So the bottleneck will be used at 1 megabit per second. So we know that S1 and S2 together will share the 1 megabit, but they will share it with a bias due to the bias of RTT. Now, the question is, what will the values be? Or what is the ratio between the values that we will have? I close the poll in a few seconds. closing. And there is an exact tie between C and D. The correct answer is C. Well, to see why, the loss throughput formula says that the throughput is inversely proportional to the round trip time. So the round trip times here are 2 plus 1 multiplied by 2, so 3, and 7, so they're multiplied by 2. So the ratio between the round trip times is the ratio 3 to 7. The throughputs will be inversely proportional, so the source 1 will receive 7/3 more than source 2, which we can easily see. You will be able to check that in the lab. We can do the experiment. We will see that you get more. And the bad news is this is how things are on the internet today. We will see next week how people have tried to fix this. But as long as you're in the regime where most of us are running in the internet today, this is the congestion control that's implemented in the internet. There have been many attempts to change that by doing an increase that's independent of the MSS or an increase that is independent of the round trip time, but none of them make it through. So there is really an impact, which is good news for the content distribution networks. That one more reason for deploying software or content distribution closer to customers. If you're Microsoft and you have to distribute new versions of the operating system, or if you're Google and you want to distribute YouTube video, then of course, if you put everything in California and the whole world would access you from California, then there would be this problem here. People that are far away will have poor performance simply because they're always competing on uneven terms with people that are closer. Right? If here you get less than twice the coding quality in YouTube, you will see that, that your code is not good enough, which would force Google to deploy much more bandwidth for those that are far away. Then at some point it becomes less expensive to put the content closer to the destination. So there is a large economical impact of this fact that is deployed today. Back to UDP applications, so applications that are not running TCP, like some form of, I'm not sure exactly what Zoom does, but a few years ago we analyzed what Skype does. It was before COVID, we were more using Skype than Zoom. And Skype tries to use UDP as much as possible. If the quality is good enough, Skype, at least the Skype we tested a few years ago, will try to use UDP because it does not have the head of the line blocking problems of TCP. Now, what should we do if we have a UDP application that's using a lot of traffic? If the UDP application is just simply like TCP, like QUIC is not really an application, but an application framework that we don't call it transport layer because of the way things are designed in the TCP-IP architecture, but in reality it is transport, so it does the same as TCP. But if you do video streaming, you don't do TCP. You don't send a packet and wait for an acknowledgement. You do smarter things. You encode with variable quality. For example, you encode one segment, a few frames at high quality, and you piggyback with it the previous and the next frame with lower quality. So if this packet is lost and the next packet or the previous packet is not lost, you will have the frame with a lower quality. And what you will display on your screen is this frame with lower quality. And if it's an isolated loss, none of us will see a difference. In 25 frames a second, if a few frames are displayed with low quality, we'll not see it. If it lasts for a few seconds, we might see a sudden decrease in quality, but perhaps we will not even notice. We'll just think I had something in front of my eyes. And so this is the tricks that are done in audiovisual coding. Of course, this is how do you put TCP congestion control in that? Where is the window? How do you reduce the window? You don't do that. So instead, you control the rate, which is back to the normal way of controlling the rate. But since now TCP has been deployed a lot, the dogma of the ITF is you should imitate TCP. So such an application should control its rate by computing exactly this. So such an application will estimate the loss probability by using things like the real-time protocol, RTP, that periodically, every second, send a report back to the source to see, here is everything I've received. The source can see what has not been received and estimate Q, the loss probability, and will calculate the rate at which it is sending by applying this formula. And it's possible because, at least with some granularity, because it's an audiovisual application that has several possible values of the rate. So this is one way of implementing what is called a TCP-friendly application, and the protocol for that is called TFRC, and this is how we would make sure we get practically the same as TCP, and therefore avoid congestion collapse and have some efficiency. Voila, that's all we will do for today. Next week, we will study other versions of TCP that do significantly different things.